Hi ladies and gentlemen, in this video we see the operation of a D flip-flop. How a D flip-flop is, we will explain how a D flip-flop is derived from a JK flip-flop. We will see the truth table of a JK flip-flop and the simulation. So let me start with that presentation. So the speech is organized in your learning outcomes, then the theory of a delay flip-flop, and its simulation in QX, then the delay flip-flop in Verilog, then the summary of understanding. So what you will learn in this video is you will learn to derive D flip-flop from JK flip-flop. Then you will learn the working model and truth table of D flip-flop. Then you will simulate D flip-flop in QX and Verilog. Now, what is a delay flip-flop or D flip-flop? A JK flip-flop becomes a D flip-flop with Jn equal to Kn complement, or that is equal to Dn. When the inputs J and K are complemented, if K is the complement of J or J is the complement of K, that is equal to some input, say Dn, then it becomes a delay flip-flop. That the second and third line or row of the JK flip-flop truth table are in play here. JK flip-flop, the truth table of JK flip-flop are in play here. That is a 0 1 condition and 1 0 condition. J equal to 0, K equal to 1, and K equal to J equal to 1. That is J with Jn and Kn are complements. The second and third line of the truth table play a role here. So that model is basically the Qn plus 1 output is Jn Qn bar or Kn bar Qn with Jn equal to Kn equal to Dn, some input data input Dn and Qn bar or Dn and Qn. So it becomes Dn and Qn or Qn bar. Qn or Qn bar is 1, so Qn plus 1 is Dn. So what is the meaning of that? That is the output after the nth clock, that is Qn plus 1, that is the input before the clock. So whatever input was there before the clock, that is transmitted to the output as such. The output simply follows the input with a maximum delay of 1 clock cycle. Okay, so this device can be used to provide a delay of maximum 1 clock cycle, and that's why the name delay flip-flop. So the truth table looks like this. These are for the D. When D equal to 0 and clock is active, then Qn plus 1 is Dn, that is 0. With a 0, with a 1, with a clock equal to 1, Qn plus 1 will be 1. If the clock is inactive, then whatever value was there previously, it will be retained there. So D flip-flop is used in data storage. It is used in registers. You use D flip-flops for creating registers. So you can observe the simulation in QX. Here you can see that this is a normal flip-flop. You can use any SR flip-flop or anything, because there is no toggling condition or rise around or anything, because J is always a complement of K. So only that last line J equal to K equal to 1 does not happen here. So you can use any SR flip-flop or JK flip-flop, and you complement this inputs. This is a J input that is complemented and given here. Some input D is available here. That is high for 20 nanosecond and low for 20 nanosecond, and you apply some clock here. You can give clear and preset, etc. You can give a preset signal here and a clear signal. You can give a preset signal here and a clear signal here, no problem, synchronous inputs. Now let us run the simulation, and you can see that here you can see the outputs. See, this is a clock that is with a 20 nanosecond period. Clock is there. So this is a D input. Initially for some nanoseconds this is ambiguous. Then it at the first clock you can see that the clock hits here. Before the clock the output is ambiguous. So here at the clock the output becomes a high. This is a data input, it becomes a high, and this 0 comes here. So when this 0 comes, it does not change because it waits for the next clock. So from here you can see this delay. This has become 0 at this point, but that gets reflected here after half the clock cycle. So you can see that this output appears at the output with some delay. So what is the maximum delay possible? That is 1 clock period. See, if a change occurs here, say if a change occurs here at this point, and I say at this point, say if some change occurs at this point, then where does it come? It comes here. Okay. So you get a maximum delay of one clock cycle. You can see that this is a complement of q bar is a complement of q. So this is how it happens. So assuming that these are positive or negative edge triggered flip flops, suppose this if I'm using edge triggering, if I use this, if the transition is happening at these edges, say suppose a change happens here, an input change happens here, then when will it be affected at the output? That will be affected here. So you get a maximum delay of one clock cycle with the edge triggered flip flops. Okay. So this is how the simulation of D flip flop happens. Now let me go back to my presentation. Now this is a circuit of a delay flip-flop. We have the JK flip-flop or SR flip-flop or whatever. I complement the inputs and give here. This is a common clock. This is a circuit we have just simulated. Now D flip-flop with Verilog, you can implement this circuit with Verilog like this. I start with a module, some name D flip-flop. Output wires are Q bar, and input wires are D and clock. Internal nets are A, B, D, B bar. Okay, D bar, that is I take a complement of the input, so it is D bar, and first NAND, that is fed with Q bar and clock and D, and output is A. So then there is an inverter for this D, so D gets inverted to get D bar. So then there is an AND gate to which I apply D bar Q and CLK, that is here. Okay, D bar Q and K and CLK, that is applied here. D bar Q and CLK, that is there, and here I apply my Q bar and A. These are the last two NAND gates where I apply these inputs A and B. Okay, you get this last set of NAND gates. Now we will run this in. This is the device, and this is my test bench. This is a device I have seen, and this is a test bench. So here, just like the previous case, I use this. I initialize to some value, then dump file, and D and clock I give. So I can run the simulation. Now you can see that with initially the clock is ambiguous, so it stays in some arbitrary state. Here with the clock is active at 5 nanosecond, with the clock active and D equal to 0, Q becomes a 0 and D bar becomes a 1. And here it is 1 at clock equal to 1 and D equal to 1, Q becomes a 1 and Q bar becomes a 0. With the clock equal to 0, again it stays in the previous value because clock is inactive. Now with the again clock 1 and D equal to 0, Q becomes a 0 and Q bar is a 1. Okay, so this is how I simulate, I model D flip-flop with Verilog. Now what you learned in this video is that you learn to derive D flip-flop from JK flip-flop. You make J equal to K complement and it becomes a D flip-flop. You learn the working model and truth tables of D flip-flop. Then you simulated D flip-flop in Qux and Verilog. And that is the end of this video. I thank you all.